So my name is Maxim Belkin, and I will talk about containers. Containers on blue waters. So how many of you know what a container, a software container is in general? OK, so good. Approximately 50% will need my first few introductory slides. So why containers and why on HPC? Why is it a problem? Why is it such a big deal? So if we take a look at any application, practically, take a simplistic view, we'll see that, oh, we have an application, some components, they work together, we provide input data, it crunches that data and produces a result. So it seems reasonable. A reasonable approach would be, OK, I got an allocation on blue waters or on any other supercomputer. What should I do? If I just go ahead and copy my program to a supercomputer, it will just not work. It will not produce the expected result. Well, it might just simply fail. So why is that? Well, you probably already know that simplistic view is not right. So our application depends on system libraries, some other executables, on the hardware, and we have to, essentially, when we bring our application to a supercomputer, what happens is that we lose all these connections. The question is what to do. What can we do? And software containers were designed or were developed, created specifically for that purpose. The idea behind software containers is that they bring the software that your application depends on with your application. So essentially, if you have your application in a software container, it has all the dependencies that it needs. I also added this area, light blue area, and I put data on the edge on purpose, because you can include your data into a container. You can do that, or you can choose not to do that and include only your application in the container. So that's clear, and you probably know some solutions that exist out there, such as Docker, that do that. Now the question is, what do we do with the hardware component? Well, and this is what I will talk about today, and we will see how this problem is solved on HPC, in the world of high-performance computing. So far, so good? OK. So Docker. Docker, you probably heard about that thing. It's a very nice solution. It's very popular. It wasn't the first one, but it's gained a lot of traction in the recent years. It has a GitHub repository, GitHub organization, and therefore you can see someone peeking on the bottom left here. Now, Docker is a great tool, but it's not suitable for HPC. And the reason is that inside of a Docker container, you can be a root. And smart people with bad intentions can exploit that. That's why Docker is a no-no in the world of HPC, with just a little bit concerned with regards to security. And as you know, Blue Waters uses two-factor authentication, so there is no way Blue Waters security team would allow that. Would allow Docker on Blue Waters. So therefore, people started working and have been working on some other solutions. And today, I will mention two solutions that currently exist on Blue Waters and allow us to use containers on Blue Waters, so in HPC. So the first solution that I will talk about is Shifter. And the second solution is Singularity. Both of these solutions, they are open source. At least their source code is on GitHub. Shifter is designed specifically for HPC, and Singularity is designed just to work on anything, but also works on HPC. So let's get started with Shifter. Yes, apologies before that. Just a brief review of what a Docker is. So Docker is a solution, and you can create your so-called recipes. These recipes are called Dockerfiles, where you just write what you want to do. For example, here I'm taking a CentOS 7 Linux, so this is a Linux thing. I execute yum update, upgrade, copy some files from my, let's say, laptop. If I'm working on a laptop, I do configure, make install as usual. Workdir is just a setting that allows us to set where we will land in a container if we execute it. I'm sorry? What fails? Well, you will not build your image. So the way it works, you create a recipe. And actually, I will. Once you have this recipe, what you do is you build an image. So to build an image, you do docker build, then -t stands for tag, so the name you want to give to your container. And just dot, meaning, OK, Dockerfile is in this directory. So dot there is just a path to the Dockerfile. Once you have an image, so this is called an image, you can upload it to Docker Hub with a Docker push and name of your container that you want to upload. You can download it later on a different machine. It can be any machine that has a Docker installed. You can run it, and this is where this workdir will come into play. Essentially, when you run it, you will land in that working directory. And finally, if you have a running container, you can open a separate shell and execute a command like in that running container. So there is a difference between containers and images. When you create something static using this Dockerfile, you create an image. When you run it, it's called a container. So that's where the word container comes from. Well, I guess it has some different origin, but that's the difference. OK, so that's Docker. And those of you who know Docker, that's nothing new. So Shifter and Singularity. Let's start with Shifter. So as you know, when we log into Blue Waters, we get onto login nodes, and there are only 3 login nodes. Now, in order to get, when we submit a job, we use qsub, we get onto mum nodes. And later on, we use ap-run, and we finally, our job lands on compute nodes. So, and you can use Shifter when you submit a job. You cannot use Shifter on Blue Waters before. You cannot interact with Shifter on a login node. So in order to actually use Shifter, you have to provide this generic resource request, gres equals Shifter 16. This is how any job, so this generic resource request is required by any job, Shifter job on Blue Waters. Okay, that's not that difficult to remember because when we submit a job, we specify lots of requests such as wall time, name, and so forth. And this is just another one that we can add. OK, so once we submit a job, how do we get to the compute nodes? So first thing that we can do is we can provide, in the same call, we can say -v. So this is that means that we are setting an environment variable, UDI, equals, and the name of our Docker image. UDI here stands for user-defined image, and this is a name that Shifter uses for its sort of images that it creates from the Docker images. Docker and Shifter images, they are different. Docker images are layered, so when each command in the Dockerfile creates a layer, and Shifter doesn't have a layered system. Shifter UDIs, they have a squash FS, so meaning single file system. So, okay, the first option that we can use is we can just use -v UDI equals and the name of the Docker file on Docker Hub. Actually, it's not on Blue Waters yet. It's on Docker Hub. As soon as we do that and we get our job gets through the queue, on a mom node, we can execute, we have to execute export cray rootfs equals shifter. So that means that whatever we do next with AP run will be executed within a container. And then we can use AP run with a regular set of options with a small addition of -b, lowercase b. So -b means that I don't want to transfer the application that I'm specifying on the command line. In this case, it's app in container, app-in-container. I don't want this application to be sent by AP run to a compute node. Some of you might be surprised. And I have to explain one thing. So without -b option, by default, when we execute AP run command, AP run takes our executable and sends it to the compute nodes. When we use Shifter and we specify -v UDI on the command line or in a job batch script anywhere, Blue Waters executes a special prologue script in the beginning of a job, which actually moves our image. First of all, it downloads our image from Docker Hub, converts it to the UDI format, and then it tells compute nodes, OK, fetch them, take them. And by the time we actually we land on a mom node, our compute nodes already have that image. So that's how we can submit a Shifter job. So that's not really difficult. Essentially, -l grs equals Shifter 16, -lowercase v UDI equals and the name of the Docker image, and that's it. Well, with the addition of a cray rootfs variable equals Shifter. OK, that's one way to submit a Shifter job. Let's talk about the other one. The other one is, again, we have to specify grs equals Shifter 16. However, this time we will not specify the image that we want to use on the command line. Instead, what we will do is we will load a module called Shifter. So Shifter on Blue Waters exists in the form of a module, but it is accessible only from the mom node. So it's not accessible from the login node here. So we can get it only on the mom node loaded. So once we do that, once we load Shifter module, we can again use AP run command, and again we use the same -b option. But this time we will use the Shifter program Shifter executable that is provided by Shifter module. And we will specify image using that --image flag. And now, after that flag, we can specify again our executable that we want to execute in the container and options. Well, you can immediately notice that here we didn't specify our Dockerfile when we submitted a job. That means that here we can use a different image later on. So this way we can use several Docker images in a single job. Okay, let's quickly talk about Shifter module that I mentioned already. So Shifter module essentially provides two commands, Shifter and Shifter IMG, stands for image. So Shifter commands basically launches our application that we have in our user-defined image on compute nodes. Shifter IMG is sort of an executable that accepts several arguments, subcommands. The first one that I will mention is images. And images simply returns us the list of already downloaded Docker images that exist on Blue Waters, and you don't have to re-download them. Lookup, basically this is probably the least useful command that tells you whether image exists on Blue Waters or not. If it doesn't exist, it returns an error. Pull, using pull command, you can download Docker images and convert them to UDI. This is all done in one step. And finally, login. This is necessary. Login, Shifter IMG login allows us to sort of log into Docker Hub to download our private images. Okay. A few examples. Shifter IMG images doesn't take any arguments. That's very straightforward. Lookup, again, just checks whether image exists or not. Shifter IMG pull CentOS latest would download the an image from Docker Hub and convert it to Shifter UDI, and so forth. The last two commands, Shifter IMG pull --user, actually allow us to pull images in a way, private images, in a way that we restrict their usage to specific users. Of course, you should use your username as the first one, and then after comma, you can add more users or groups. Okay, so let's go back to this image. So far, so good. We talked about how Shifter sort of brings all the software with it, and it basically acts similar to Docker. Now let's consider that hardware part. So definitely we cannot bring hardware with software, with Docker, with Shifter, so we have to do something else. And for that purpose, Shifter uses two things. So there are two hardware components that we are interested in. Interconnect, so that we can run our MPI applications, and GPUs, so for data analytics, whatever. Let's take a look at that. So let's consider MPI. What do we have to do in order to be able to run MPI applications? First of all, our container has to have a recent glibc. So you cannot use CentOS 6. I know one of the CIS group members knows how to sort of get around that, I guess. But this is it might be possible to avoid that, but it will be hard. The second requirement for the container is that we have to have, in that container we have to have an MPI implementation, basically which is one of the following 6 in this case. So there is a so-called MPeach ABI compatibility initiative, and what it means is that certain MPI implementations, they are ABI compatible with each other. So if we use one implementation in the container and ABI compatible implementation and ABI compatible but a different one implementation on Blue Waters, they will understand each other. So they will be able to communicate with each other. And finally, the suggestion is not to use package managers to install MPI, even though some of them provide MPI. But again, this is actually not a strict solution, not a strict requirement, I'm sorry. And there are ways to get around that third option for sure. And if you have need in doing that, you can contact Blue Water support. Now, so we talked about requirements for the container. There are a few requirements for the Blue Water system. And the first one is that we can use only 2 programming environments, Intel or GNU. So we cannot use Cray programming environment. The second one is that we have to, again, have MPeach ABI compatible implementation on Blue Waters installed. Or loaded, I should say, because it is already installed in the form of a module. And finally, we have to do some small trick with the LD library path that I will describe in 2 slides. OK, so Dockerfile. I mentioned that we should have a recent version of glibc. So CentOS 7 has version that satisfies it. Then we run here some commands. And this is actually a code snippet that installs MPeach version 3.2. So you can use that version you can use 3.2. There is a more recent one, 3.2.1. You can install it in your container and therefore use MPICC to compile your application, and it will work. So that's Dockerfile. The next is job batch script. So that secret thing about LD library path. First that we have to do is, again, we have to unload Cray environment because we cannot work with it. Well, you can read it. Here we unload that Cray environment. We unload campus cluster compatibility environment. Then we load GNU programming environment and load finally this module load Cray MPeach ABI. We actually load ABI compatible MPI implementation. Now the tricky part is here is shown on lines 7 through 10. What we do here is essentially we copy libraries that we have to a special folder that we prepare for our simulations. I suggest that you just have a look at it and sort of, if you need help with that, contact us. Otherwise, I'll just move on quickly. So, and this is the trick here. We export a LD library path, and that's it. So once we do that, we can submit a job. Again, this is the first way to submit a job. Here we don't specify image on the command line. And the other one is when we specify image on the command line. As you can see, as I already mentioned, the advantage of the first approach is that we can use several images in a single job. But let's discuss the caveats here. And this is the work that we actually recently did. We computed the job startup time. So let's say you have a job in which you start your Shifter application in a Shifter container many times. Well, basically, the top graph shows that it doesn't matter, the size of your Docker image does not matter. And the second one shows us that if you provide an image, if you specify image when you submit a job, essentially your job will start immediately. So there won't be an overhead when you use ppn, let's say, equals 16. As you can see, the difference is noticeable. Okay, we also tested performance of MPI applications in Shifter, and performance is identical in terms of MPI. MPI behaves identically, and input-output, they are also the same. So basically, Shifter does not impact performance of applications. Now, GPUs, the first requirement to use GPU is that we have to use a command line interface, so meaning that Shifter command. Therefore, we can specify image only with a -- image flag. The other one is that we have to set the CUDA visible devices. So CUDA visible devices in general is a comma separated list of GPUs that you would like to be involved in that Shifter job. But on Blue Waters, XK nodes, they have only one GPU. Therefore, the only value that we can provide is 0. On other systems, you might be able to, if other systems have more than one GPU, then you would use 0, 1, and so forth. So our call to basically Shifter application would look like that, ap run -b. So -b is very important for Shifter jobs. And then other options, which I skipped here, then -- meaning the end of options for the ap run command. And then you see Shifter, and so forth. We specify image. This is how we would run a GPU-enabled job, essentially. The caveat here is when we combine MPI and GPU. The problem is that Shifter command removes LD library path, which is important for MPI. So therefore, to solve that, we have to use a small trick. What we have to do is instead of just using our application on the command line, we have to use a script. And in that script, we have to somehow restore LD library path. That's all. And the way so what I did here, I just set that variable right in the call, in the ap run call. But you can do it any other way. You can save it to a disk or so forth. There are many ways to do that. So basically, this is how we can combine MPI and GPU in Shifter jobs. And we already had an application that did that on Blue Waters. Directory mapping. By default, projects, Scratch, and home directories are mapped from Blue Waters to user-defined images. But you can add additional, you can create additional mappings with the caveat that, to actually create that additional mapping, we have to use --volume flag for the Shifter, to the Shifter command. But the caveat is that the path in the UDI must exist when you create that mapping. And then on the bottom, you see the second syntax to create that mapping when you submit a job. Basically using a single -v flag, but that second -v flag has a different meaning from the qsubs one. Now, Shifter. And I know that we spent a lot of time on Shifter. I apologize for that because Singularity is much easier. OK, so for Singularity, we have to specify a generic resource request. And I was going to ask Galen to prepare to open the door so that I will be able to run from it quickly. So how do we get to compute nodes? Module load Singularity on a mom node. The next step is we have to build an image. We have to build a Singularity image. And this is how you would do that. The caveat is that currently you have to do that on your computer. You cannot do that on Blue Waters. And then you just execute Singularity exec -h. So -H creates changes home directory. Sort of here we are setting -u to on Blue Waters to home in our Shifter in our Singularity container, and that's it. So the image that we have just created, and then the application within that image. This is how we can run Singularity containers. Again, directory mapping essentially is just a flag to the exec command, -b, capital B. And Singularity, unlike Shifter, doesn't care if directory exists. It will create it. And below you see a note that projects on Blue Waters corresponds to MNT ABC projects in a Singularity. So pay attention to that when you use Singularity. To use GPUs, all we have to do is --NV flag. Again, this is contrary to Shifter, where we had to do some tricks. Again, here the only caveat is that we have to, if you plan to use GPU-capable executable GPU sort of, let's say CUDA executable that exists on Blue Waters file system, you have to sort of map it to your Singularity container using a -B flag. And here I'm showing an example where I execute an NVIDIA SMI. All I do is I just use that -B flag, and that's it. And then I just execute SMI. And again, I skipped --NV flag. I apologize. So that --NV flag has to be in that line there. That's it. So Singularity supports MPI by default, and thank you very much.